Right. So your written test number 2, the result has been released. If you want to discuss any question there, please come by. It's just that I don't have office hour today, unfortunately, but Tuesday, Wednesday, Thursday, anytime you like, just usual time, 3 p.m. Your lab number 4, that'll be the last lab. It's also important to actually do it. And I'll try to give you a little bit highlights maybe on our last class on Wednesday. Thank you, Dave. Okay. And then there's a bonus opportunity. So for course evaluation, completely anonymous. If you're interested, go ahead. And there's some deadline for that. So please watch out for that if you're interested. Okay. And office hour, sorry, no Monday today. But if you want to talk to me, Tuesday, Wednesday, Thursday, the usual time. And if you want to reach out to Andy just about the lab, you can also feel free. Okay. All right, so any question about the course? So Wednesday will be the last class, so I will also talk a little bit more about the exam on Wednesday as well, right? That'll be the last class. And your exam will be next Thursday, quite soon. So I think we should also do at least one review session to answer your questions. I think we can do, maybe over Zoom, just to make sure everybody can attend, well, as many as possible. I'll also record the session as well. I'll reach out to you about the time. Do you guys have any preference about which day? Next week? Okay, so maybe I'll just choose maybe 1 or 2 days then. Okay, I'll let you guys know. If you do have some preference, do let me know beforehand. For example, it might clash with your other early exam. I can definitely try to avoid it. You can let me know. All right, quick recap. So last time we did more exercises. Number 1, we did it on how to formulate natural language into LTL, right? We kind of discussed the different alternative. You want to review the details and make sure you kind of know which one to choose. And also, if I give you some alternative, you should also try to justify whether it's appropriate. If it is appropriate, show it. If it is not appropriate, you got to give me some counter example, right? Things like that. And we did 2 more exercises on the until, we can tell, and release operators. So these are the last 3 operators that we're going to need to know for LTL, right? Just going to make sure. On the exam, you will be allowed for one-sided data sheets. You can handwrite, you can computer type, whatever you like. You can put whatever information you like on the sheets. And if I were you, I will put some formal definition there for the operator, just in case you forgot, right? You can also put any insights that we mentioned about the operator on the sheet as well. Whatever you like, there's no restriction.
Professor?
Yeah.
Just to confirm, one-sided.
One-sided. 1.
Is that a font size?
Well, I would say about 10. Okay. Yeah, I don't want to make it too small. You don't want to put the whole course into a single-sided sheet, right? I don't think that's a good sign. You want to put just enough there so they can remind you about the details.
What if it's handwritten?
Handwritten is fine. No problem. Yeah. You can do computer type. You can do screenshots if you want to do handwritten, or you want to collaborate with your classmate and share the sheets. That's also fine by me. All right, no restriction. In some way, it's really a way to kind of also push you to put the most important information by being selective. That's also a good way for you to study as well, right? It's really the goal. All right, so these are the 2 exercises you guys can review and let me know. And for the optional exercises over there, I'll give you the solution a little bit later, right? Hopefully by the end of this week. You can also compare your solution to that. That can also help. And then we started with this only single page to move transition to a new lecture about program verification. We'll dive much deeper into it today. But before that, you guys have to remember, what do we really mean by assertions being weaker versus stronger? So stronger if the assertion is going to allow strictly fewer values to be satisfied. It will be weaker if that can allow strictly more values to be satisfied, right? Weaker versus stronger. We're going to need that concept today when we define the so-called weakest precondition for program verification. That's something we're going to dive into. And we talk about the strongest assertion will be just false, allowing nothing. And the weakest one will be just true, allowing everything, right? So that's something you want to really make sure you kind of get the idea. And that we'll review again today, right, as we see more use cases. Are we okay about stronger versus weaker in general? Okay, ask me more if you want to. All right, so let's now dive into program verification. Let me just start with, again, we are basically still talking about weaker versus stronger, but I want to put the context a little bit closer to the algorithm that we are familiar with, in the more TLA plus kind of syntax. So that's kind of the example you will see on the slides as well. Okay? And today, I will mostly stay on my iPad to give you guys the example walkthrough, but as you will see the slides, there are also texture points you want to also catch, right? That's pretty much consistent with what I'm going to talk about. But there will be some critical points I can run through the slides very quickly. But let's now focus more on the iPad for today. All right, let's now just see the general structure for algorithm, okay? So we're gonna adapt the assertions into either pre or post condition, right? That's basically what you did for lab 2, also both of your programming tests. So let's say we got a general structure for some algorithm, and just a foo, very general one, okay? And then before the actual code, we can say assert, and this will be the precondition, all right? So this will be the precondition. Of course, you may get more than one, right? So just putting one, just for example. So this is the precondition, okay? I'll talk about some special cases in a moment. All right, so that's a single assert. And then we got, of course, some algorithm code over here. That would be your implementation, okay? So this part here will be the implementation. And then we got multiple assertion over here. That would be the post condition, right? You can think about ending section here. We got multiple assertions. I'll just put one here. So this part will be the post condition. All right. So let's now talk more about what does it really mean when the precondition is stronger versus weaker, and also the post condition being weaker or stronger, right? Let's talk a little bit more about it. So post condition here, let me also write it down. So this will be the post condition. All right, let's start with the precondition. So for precondition over here, for example, you might have, let's say, x larger than 3 versus x larger than 4. In some ways, it's more like a choices for you. Which one do you really want to be the precondition for your algorithm? And you guys can simply try to see which one's weaker and which one's stronger, right? Okay, I'm pretty sure. And if you agree, this one here is a weaker one. And this one here is relatively stronger because you got less values, fewer values satisfying this, right? You can try to draw the diagram or try to prove the implication about it, which we did last time, right? For that one, I'm going to leave to you. So what does it really mean? Okay, your precondition here is actually weaker. So we can just say a little bit more. So that means more input values will be allowed for the computation of the algorithm. So that means more input values allowed for the computation of the algorithm. Right, so you just kind of compare which one's weaker, which one's stronger. So if you actually choose this one over here, which is a stronger one, there will be a certain value of input that would not be allowed. For example, if you look at this one here, for example here, let's say x equals 4 will not be allowed because it's not larger than 4, but it is larger than 3, right? Not allowed. And let's talk about extreme cases. For the precondition, the weakest precondition you might have is true. That's the weakest. That means no constraint on the input. Any input is fine. Okay? Any input are okay. So that means your algorithm can take any input. On the other hand, what if the precondition is actually false? The other extreme. That means your algorithm is so picky, no input values can ever be taken. Okay? No input values are acceptable or accepted. You definitely don't want to have the false as the precondition, even though, as we'll see later, somehow if you have the precondition false, your program can be argued to be correct automatically, funny enough. But that's something we'll see a little bit later. Okay? But for true, it might be okay because maybe you don't really constrain any input value. That might be fine, but definitely not false in practice. All right, that's about precondition. What about postcondition? Similar idea, but we're going to think about more about output value. What would be acceptable, right? So here, let's say the post condition, it really defines the set of acceptable output values. Okay, let's just make it a little bit more general. Okay, so let's say if you got, let's say, post condition 1 and also post condition 2. If somehow you can show that P1 as the post condition is actually stronger, and somehow this one here is actually weaker, right? If you're able to show that, what does it really mean when you actually choose P1? If you have chosen P1, it's a stronger post condition. That means strictly fewer output value will be acceptable as the algorithm, right? Output. Fewer output values acceptable. On the other hand, if you actually choose the weaker post condition, in that way you're allowing more output values to be accepted, right? Which one you choose in general is kind of up to your application, right? Okay, let's now talk about extreme to also understand a little bit deeper, okay? So let's say we talk about the post condition over here. Now, let's say I got true over here and also I got false over here. Let's say you are the developer of the algorithm. Which one would you rather hope being the post condition? We're thinking this way, which one is going to make your life easier if you're the implementer? Would you rather the post condition is actually true or is false? Adrian?
I would rather a weaker post condition because that makes it easier for me to make it true.
Make it true, exactly. Yeah, in this case, let's say the weakest one is true. That means it doesn't really matter what I produce, it's always acceptable, right? So this means any output is acceptable. This would be good for the implementer, but for me as a customer, I would rather not. This is a post condition because that means there's no constraint on you in terms of the quality of output you are delivering to me, right? On the other hand, the false over here is actually very, very strict. That means nothing is going to satisfy the customer. Nothing. That's also not good, right? We don't want to really go for extreme. This means no computation can produce acceptable output value. Because anything you produce, post condition is false anyway, right? So in practice, for post condition, you don't really want this one here because that one doesn't constrain on the implementer. And this one here is constraining the implementer unreasonably. Okay? You don't really want these two in practice, but theoretically we can discuss them to see the extreme. But for the precondition, you don't want this false over here in practice because it's not going to allow any input value to be computed. But this one here might be possible if you actually want to calculate any input values. That might be fine. Okay. All right, so this page here is just to kind of show to you how we can adapt the idea about being weaker versus stronger, and the assertion can either be precondition or postcondition, right? It's going to help as we go a little bit deeper. Okay. All right, any questions? We good? All right. Let's now consider some example, right? So the example I'm going to talk about basically is on slide number 6 and also slide number 7. I'm going to talk about these two. Okay, let's now dive into them. Pretty simple, okay, but it can illustrate some good points. All right, so let's now talk about this one here, right? So let's say the algorithm is we want to increment the value of I by 9. Simple one. And then we have some precondition over here. We have some postcondition here. And the implementation is just a single line. All right, let's say that's what we have. Before I ask your input, let me just annotate very quickly something. Okay, so apparently this is a precondition, right? And this is the postcondition. And we say that these two together, pre and post condition, so these are the so-called specification. These are the specification. Okay. And we say that whenever we talk about correctness, it's really relative. You're basically asking, is my algorithm over here about incrementing, is it really correct? You cannot really say it's really correct absolutely, like under any circumstances. It must be somehow relative to what kind of precondition and postcondition that's given. It's kind of relative. Okay, so that's a very important concept which you will also see on the slides. So when we talk about program verification, let's clarify what we really mean by correctness. Let's clarify this first. So whenever we talk about correctness, so number one is relative. It's a relative concept. Okay, and then let's now give a little bit more precise definition. We're saying that for input values satisfying the precondition, okay, input value satisfying the precondition, if we try to execute whatever lines that's within the implementation, which might involve variable assignments, might involve if then else, it might involve loops, right? All these kind of concepts. Executing the implementation well. Okay, so now we're going to define what it really means by correctness. Guys, take a guess. What kind of criteria do we need to evaluate whether or not, given that the input already satisfied the precondition, and now we're executing the implementation, what do we need to judge in order to say that the algorithm is actually correct? There are two things.
It's like a local post condition that satisfies at every point after every execution.
So you want to make sure.
Invariance.
Yeah, sure. Yeah, let's not worry about invariant over here, right? We'll talk about algorithm isolation. So what you're saying is post condition should be satisfied. I agree. There's one missing bit.
You need to stop the algorithm. It needs to stop.
You need to terminate.
Terminate.
Okay,
Then
good.
when it terminates, it needs to satisfy the last condition.
Exactly. Okay, so there are two things over here, which you guys completely got it right. Number one, it will terminate. I can tell you that termination is only a concern if you got loops involved. If you only got variable assignment, termination is guaranteed. If you got only if then else, it's also guaranteed, right? Okay, and number two, upon termination, the output-input combination will satisfy the post condition, right? The output-input values satisfy the post condition. Okay, sounds straightforward. Okay, let's see. We got post condition here, and also we got the precondition over here, right? If you don't really argue anything about termination, as you will see on the slides, it is something called partial correctness. As we'll see, so whenever you give us an algorithm, you're saying, okay, let me not focus on the termination part just yet. I only want to know whether the produced value is going to satisfy the post condition, as we'll see later. Sometimes when you're given the loops, you don't necessarily have to prove about termination right away. You can just try to see, based on the loop structure, is the output, assuming that it terminates, is the output going to satisfy the post condition? It's a separation of concern, as we will see on the slides. Okay, partial correctness is one. And if you combine 1 and 2 all together, that means you're going to prove these two separately. 1 and 2 is called total correctness. So partial correctness plus termination will be total correctness. That's how you can put it, right? It's also on the slides. All right, any question here? All right, let's now move back to this particular algorithm over here. Okay, I'll move a little bit closer. Do you guys think this algorithm here is going to satisfy the correctness criteria? If no, give me some counterexample. Adrian, go ahead.
No, the precondition will be satisfied with the postcondition.
Yeah, exactly. Okay, very nice. Okay, but this is actually very easy to spot. But as the program gets a little bit more complicated, we'll need some systematic way to reveal that, which I'll show to you. Okay, but just some motivating example. So what Adrian was saying is completely spot on. If you look at this one here, we say that this precondition is too weak. It allows I equals 4. In which case, if you try to see I4, 4 plus 9 is going to be 13. 13 larger than 13 is false, right? Okay, too weak. It's going to lead to postcondition violation. So we're going to see later, how do we actually have some precondition that is not too weak in order to guarantee any acceptable input value is going to guarantee you're going to satisfy the postcondition. That's something we'll see a little bit later. Okay, let me recap very quickly. Okay, so we talk about correctness. Number one is relative to the specification you have, which consists of precondition and postcondition. And then we talk about either total correctness or partial correctness. So total correctness is really partial correctness plus the proof about termination, which we'll see on Wednesday in the last lecture. We just need to introduce an idea about variance for the loop. And this particular algorithm over here is not correct because given the specification, especially for the precondition, we might have some value that's allowed by the precondition. That means it's too weak. And that particular allowed input value is going to lead to postcondition violation. So we say it's not correct. Okay? And we'll see a little bit more later. All right, so now another one here. Guys, how about this one here? Again, let me just annotate again. So we got precondition here, and we got postcondition over here. Do you think this algorithm here is correct, given the specification, right? Did it look good? Yeah. This one here actually has no problem, but it does require a little bit of discussion here, which I'll point out. If you think about over here, given this precondition, allowable input values would be, for example, 6, 7, 8, 9, 10, etc. Right? And then if you actually try to execute the implementation over here, that means I is going to become 15, and then 16, 17, etc. All of them is going to satisfy the postcondition. So this nicely satisfies the correctness criteria we talk about. No problem. However, it will be worth our attention and think about, is the precondition here too strong? In the sense that, okay, I'm going to put it here. Is this precondition too strong? In the sense that, does it disallow certain input value that wouldn't lead to postcondition violation? The value I'm talking about is, what about I is equal to, let's say, 5, right? You can see I equals 5 plus 9 is going to be 14, which is going to satisfy the postcondition. However, the precondition as is not going to allow I equals 5. So this is more like a design question. Should you allow I to be included in the precondition or not? It's completely up to your judgment, right? Okay, I'm just gonna highlight this. Okay. So I'm going to visualize exactly how these two programs will compare. So this one is correct, but it's debatable about the precondition being too strong or not. And the previous one is just incorrect because the precondition is too weak. Okay. This allowed input value actually would not cause any postcondition violation. Postcondition violation. Right, so whether you want to change the precondition or not is completely up to you. All right. All right, any question on here? All right, I think enough warm up. So now we're going to introduce something called Hoare triple or predicate transformer to actually show to you how we can systematically, based on the specification, which is the precondition and postcondition combined, and also the algorithm, how can we kind of formulate something for us to play with mathematically? Okay, that's something we'll see. All right, and let's see, on the slides, we are done with slide number 6 and slide number 7. Okay, and so this slide over here is just about, oh, actually, I think that one is already about Hoare triple, right? You will see this syntax here. I'm going to talk about it right now. Okay, let's now talk about it. Hoare triple. Okay, by the way, just for your reference, Hoare over here is a prominent researcher by the name of Tony Hoare. And you guys have already used his work before in 2101. He is also the inventor of quicksort, the same person. He's a very prominent researcher on software engineering and computer science. So what we're talking about is just two of his most prominent work, right? Quicksort and Hoare triple. Okay, just for your reference. All right, let's now talk about what a Hoare triple would look like. Let's talk about the syntax and also the semantics, I mean their meaning, and then I'll show to you, given a piece of program, how we can transform the program into a Hoare triple, right? That's something we're going to do. Let's start with the syntax first. And the syntax looks like this. Because it's Hoare triple, right? There are 3 components in the triple. So we got something here, curly brackets. Okay, and then we got something in the middle. Just underline. It's not really a part of the syntax, just saying there should be something in the middle. And then we got another curly brackets. So what you want to remember is this part here is the first part of the syntax. And this part here is the part 2 of the syntax, okay? And there will be something in the middle. Okay, let's talk about them quickly. So what's really inside over here will be your precondition for the algorithm. Precondition is a predicate. Okay, and then this part over here will be the postcondition, also a predicate. So you can think about if you got multiple assertions as your precondition or postcondition, you would just say precondition 1 and precondition 2 and precondition 3, etc. Right? Just put them into conjunction. Okay. And what's in the middle is the programming statements for the algorithm. So programming statements, which will be variable assignments, if and else, and also loops. So that's the syntax that we're going to see a lot in the lecture. And then the whole thing over here called a Hoare triple, they can be turned, once you formulate a syntax like this, the whole thing can be transformed into a predicate. Into a predicate. And once you move to a single predicate, we can kind of go back to our math review lecture. Given a predicate, you can actually prove or disprove it being a theorem. Okay? Which can be either proved or disproved. All right. Let's talk a little bit more about the meaning. Okay, so this is just a syntax, right, to see the different compartments, but we're going to see example very soon. But let me talk about semantics, the meaning. Okay, the Hoare triple looks like this, right? So you got your precondition over here, and also you got your postcondition over here. So let me say the postcondition is a predicate called R. And the precondition is a predicate called Q. Just convention, Q and R. Q and R itself can be a conjunction as well, right? Can be arbitrarily complicated predicates. And let's say the programming statements we have is S. Okay, programming statement, which can be as complicated as maybe shift to the right, or it could be some binary search, or whatever you like. Okay, just a programming statement. Okay, again, it's very important for you to remember these two are the predicates. But this one here is not a predicate, it's just a programming statements. But somehow, how can we transform this guy over here into a predicate? That's the issue we're going to run into. All right, well, we'll see. So let's see what the meaning is. Starting in a states, or you can think about pre-state versus post-states. Satisfying the precondition Q, satisfying Q, executing the algorithm S. Well, number one, terminates in a states, and number two, that particular state where we terminates. Oh, you cannot see that, right? Okay, so I will try to be a little bit more careful here. Okay, let me just temporarily move this one here. Okay, so you guys can see it. Okay, once you take the notes, I can move them back. Okay, so first of all, it should terminate in a states, and then that states or post states. Satisfies the post condition R. Right, so that's the meaning. Okay, so that's good. So let's say the definition, well, okay, so you can go right here. Okay. Let me see anything else to say. Yep. So you want to make sure, first of all, we got terminates. That's some proof obligation number one. And also the post state satisfy Q, that's like a proof obligation number two. In order to be correct, you want to make sure PO1 and PO2 are both right. Okay. So we say PO1 and PO2. Both of them, if you can argue both of them, so that means you got total correctness. All right. And we'll do example right away. We can revisit the two examples that we had and try to see how it can be turned into the whole triple. Okay, let's see that right away. Okay. So why don't we revisit the two? Okay, I'll just show you one here. Okay, let me go back here. Okay, example one, example two. How do we formulate a whole triple? Right? Basically, precondition here, post-condition over here, and implementation here. Right? Easy to fit in. Over here, the whole triple goes like this. Precondition is I larger than 3. Implementation is I assign I plus 9. And then the post-condition is I larger than 13. So that is the corresponding whole triple. And we'll show to you, given this whole triple, how do we prove that this whole triple is actually a theorem? We'll see that. We haven't seen that just yet. Okay. So the most important part about this exercise here is, given any arbitrary program with the specification and the implementation, how do you turn that into the whole triple, first of all, syntactically? Okay, let's do one more. Okay, what about this one here? The whole triple will be, again, precondition is I larger than 5. Implementation, I is assigned I plus 9. And the post-condition, I larger than 13. Right, so that's the whole triple. And of course, as the implementation gets more complicated, the middle part is going to get fatter, right? So it depends. Okay so far? Okay. And then the next bit is to really talk about something called the weakest precondition, right? Let me do a little bit more, and then we can take a very short break. Let me talk about maybe only these 2 pages. Okay, I think that'll be a good one. Okay, let's talk about 2 more pages, and then we can take a short break. Maybe 10 minutes or so. All right, that's the syntax, and then, okay, proving correctness. Okay, let me see this. Okay, I think this one is fine. Okay, we can skip that one. That one I already covered. Okay, just this one here. All right, so this is very important. Okay, so if you look at this part here, just this part. This part here, we got the precondition, we got the programming statements, the algorithm, and we got a postcondition. How do we prove this whole triple over here is actually a theorem or not? Let's now just highlight, select this one here. So we want to know whether it's a theorem or not. In order to prove that, this is what we have to do. Okay, this one here. All right. Overall, we want to prove something about an implication overall, right? As you can see, we got some implication here, right here. You can see the precondition is right here. The postcondition is right here. But somehow we got something called WP. That's something we got to learn. This class and also next class. All right. Let's now look at the WP first of all. Okay. Okay, let me put it right here. The way to write it is WP, and then it takes 2 arguments, number 1 and number 2. The second argument is always a predicate, and typically it's the postcondition. And the first argument here would be some programming statements like algorithm. That's typically what you should really put as the first and second arguments. And overall, WP is itself a predicate. WP is also itself a predicate. Sometimes people like to call WP a predicate transformer in the following sense. I'll write it down first and I'll explain to you. It's called a predicate transformer. And then, so here we're going to have the postcondition R over here. And also we got a programming statement S. It is a predicate transformer in the sense that given the postcondition and given the implementation, which is supposed to somehow establish some post states that's going to satisfy the postcondition, okay, it's going to give you the weakest precondition from which you can execute the statements, and assuming that it terminates, it can give you the postcondition. Okay, I'll write it down. So before Wednesday's class, this will be the part you really want to review carefully. That's about the definition for WP. Okay? WP will be the weakest precondition satisfying which guarantees that executing S will reach states satisfying R. Okay? Yeah, you can copy down the definition first, and then we'll try to visualize what's happening here. It is the weakest one. That means anything that's weaker than the weakest precondition is not acceptable. But anything that's kind of stronger than the weakest precondition is still okay. Just remember this kind of highlights, which will make more sense as we see more example. Right, you can digest the definition a little bit more before Wednesday, but let's now visualize what's happening over here. Okay? Let's say this. Let's say we got our programming statement over here. And we got our R over here, the post condition, right? So think about these two are the inputs to the WP. We got S over here, we got R here. We got the S over here, and also we got the R over here. Given these two things, we can calculate what would be the weakest precondition for us to start conceptually. If you start in the weakest precondition, any states from here is guaranteed to execute the programming statement and still satisfy the post condition. Okay? Yeah. So think about what we have is WP is actually calculated based on S and also R. So given this, which is here, given this, which is over here, if we calculate WP, which I'll show you how to calculate systematically, let's just say we have that already. Once you calculate the WP, conceptually, it is the largest set that's going to consist of all the values of input that's guaranteed. After X being executed by the algorithm, the output will just be correct because the post condition is actually satisfied. Okay? Any input value satisfying the WP of SR is guaranteed to lead to post condition satisfaction. So this is the most important insight. Guaranteed. All right. You know what? If you don't mind, I can change the color of that. It could be a little bit better. Now, the actual precondition over here is actually stronger than the weakest precondition. This will be considered as acceptable because any input over here is still an input of WP. So it's guaranteed. If you try to execute an algorithm, it will still guarantee to have the post condition satisfied. Okay? So this Q over here, if the actual precondition is stronger than the WP, okay? So stronger, you can see in the sense that you can see this is a strictly smaller set than WP, right? We kind of talk about the predicate being stronger. If this is stronger, that's okay, because every state in here is still a state in WP, which by definition is not going to lead to any post-condition violation, so we're fine. The next page, I'll show you one scenario where the precondition over here is actually even weaker than the weakest precondition. That's not good. All right? Which is okay because each input satisfying Q still satisfies the WP. Okay, so this is another important insight you want to review. Okay, it might sound still a little bit abstract, but that's something we'll see more examples to kind of reinforce. But I want to mention all the high-level insights at one go. That will help. Okay. All right. Let's see one case where it is incorrect. Okay. Hopefully that will give you a little bit more clarification. Guys, I want you to compare. Sorry, before that, Faris, go ahead.
Why does Q have to be a proper subset and strictly less? Can it just be WP itself?
It can be WP itself. So here, just for illustration, I'm just saying, okay, so to be more precise, good question here, doesn't need to be a proper subset, doesn't need to be. So as long as you can show Q implies the WP of SR. That's exactly what this one is telling you. Assuming that we are able to calculate the WP, and your precondition itself is actually no weaker than that, then we are good. No weaker than. Okay, it's a very good question. Yeah. Let's see something that will represent an incorrect program. Let's see. I want you to compare this diagram here, okay, right here, with this one here. Do you spot the difference? Let me do it again. This is correct, but this one here is incorrect. All right? The reason is the WP that we calculate, this will be the weakest one. That means every input value over here, each input here is guaranteed to lead to post-condition satisfaction. However, if your actual precondition is weaker than the weakest precondition, you're in trouble. Because, for example, let's say this value over here, valid input, but it's not part of the weakest precondition. That's not good. Okay? Valid input, but not satisfying the weakest precondition. Meaning that no guarantee, or you're going to lead to some post-condition violation, basically, right? So that means post-condition violation is expected. All right. Any question so far? Take some time, right, to digest. But I kind of want to go over some visual stuff, and then we can take a very short break by taking attendance. After that, we can do some concrete example, and then I can talk about how we calculate WP precisely. We'll get there. Okay. Okay. Why don't we take a short break by taking attendance now, please? Okay. So before the break, let me remind you very quickly. So we basically talk about two scenarios. We talk about the correct program would be when the actual precondition is stronger than the weakest precondition. That's the correct program. That's exactly what this implication is talking about. So before Wednesday's class, really try to appreciate or understand exactly what this one here is saying. It's going to determine how you understand about all the subsequent exercises, right? And this, on the other hand, tells you what an incorrect program will look like. So that one tells you once you calculate the WP, you actually will accept certain input value based on the current precondition. That one there is cannot guarantee anymore. You're going to lead to some post-condition satisfaction, most likely violation actually. So this will be incorrect. Let's see how we can apply these two scenarios into the little program that we also discussed before the break. Right here. Okay, let's just revisit them. Okay, so if you recall, we said that this one here is too weak, right? That's what we said earlier. This one here is actually too weak. And we still haven't talked about exactly how to calculate WP. We'll do that very soon. I just want to link these two examples right away to our visualization. Okay? And for now, let's take it for granted. Okay? Let's say given our post condition right here, I larger than 13. And also we got our implementation, which is I is assigned to I plus 9. Okay, that's the implementation. The WP calculation is going to be something like that. WP of, remember we put the first argument, the code, is assigned to I plus 9. And the second argument is going to be the post condition. And let me tell you the answer right away for this WP calculation first. And we'll see exactly how to calculate that. This answer is going to be I larger than 4. That one there is going to give you I larger than 4. Okay. So again, WP, the predicate transformer, given the post condition and given the implementation, what would be the weakest precondition for us to start so that we can guarantee the post condition will be satisfied? And let's say the WP is simply I larger than 4. We assume. Okay. So I larger than 4 is really what we're going to put here. And then in order for the program to be correct, we want to make sure the current precondition you have chosen for your algorithm cannot be weaker than the weakest precondition. In this case, it is weaker. The Q here is actually I larger than 3, which is weaker than I larger than 4. So that's not good, because it does allow a value over here, for example, I equals 4. And if you try this value here, it's going to give you post-condition violation. All right. Okay, so we'll do more exercises to emphasize this. Okay. Any part you want me to repeat, or is okay for now? Okay for now? Okay. This will be the incorrect. So in this case, when we try to say I larger than 3, which is a precondition, implies the WP of I is assigned to I plus 9. And then we got the post-condition over here, I larger than 13. And we say we assume we know how to calculate this. And let's say this one here, I tell you the answer, simply I larger than 4, right? But this implication here is simply not right, right? Because you cannot show that this is stronger than that. You cannot, okay? So this one here doesn't hold. That means the program is incorrect. Incorrect. Okay, one more example, and then we'll show you exactly how to calculate WP. Let's say this one here, right? We still have the same implementation and post-condition. So this one here, if we calculate WP, I plus 9, and larger than 13, and the answer is like before, simply I larger than 4. And now, what we do is, the precondition over here is I larger than 5, which is right here. And the weakest precondition, I larger than 4. We can show that I larger than 4. Would you agree? This one is stronger, right? Logically. We can easily show that. So this one holds. So that means the program is correct. Okay. The program is correct. And now we should really define how you can calculate WP. Okay. So let me show you some little bit slides over here so you can see where we are. Okay, so you want to look into Hoare logic. That's something we said earlier. You can definitely review partial correctness, total correctness. We already talked about it before the break. And then, so these are just different extremes about precondition and postcondition, also which we also set before the break, right? You can also look at the textual description. Okay, so we can now talk about the S over here, right? So the Hoare triple here, the middle part is about the programming statement, what you write the algorithm with. We got variable assignments, which we're going to talk about first. Also, you might get alternation or if then else, basically, like an if conditional. So these two are at least we want to cover today. The next one will be sequential composition, slightly more complicated, but it's not too bad. And the final one will be loops, which definitely we have to cover more on Wednesday. All right. So these four are the possible structure for, when you think about syntax. When we talk about LTL, we talk about it's a possible syntax. And here, if you talk about algorithm, it's also the possible syntax. You got variable assignment, you got if and else, you got sequential composition, you also got loops. So these are the things we're going to use to write our algorithm. All right. So let's now dive into the first WP. Also, I'm going to talk about some convention here quickly. So one typical Hoare triple you might see is something like this. So let's say we say this. Let's say we have a variable called b. B0, for example, larger than A0. And then we say B is assigned to, for example, B minus A. And then we say B equals B0 minus A. That's just one example, right? I just want to talk about what B0 here really is. So we say the B0 over here is the pre-state value. Beg your pardon. And the B here is really referring to the same variable. And that one there is the post-state value. So what you can think about is, well, I'm pretty sure you have seen this diagram before in 3342. So whenever you try to execute some algorithm, it's like a transition you're doing, right? So we got a pre-state and we also got a post-states. And the transition here might just correspond to the program itself. Let's say B is assigned to B minus A, right? That's a transition. And then we say that in the pre-state, we can refer to the variables, let's say A0, A1. And in the post-states, we can refer them as A and also B. Pre-state and post-states. Okay, a quick summary here. So in 3342, we talk about basically pre-state B and the post-state B prime, right? But we don't use that notation here. But what we use here is we simply say B0 and then B, right? So I want to clarify that. So you wouldn't see anything like a B prime in this course, but just see B0 versus B. Okay.
So would that be B0 instead of A1?
Which one?
In the 3.
Absolutely. Thank you. I agree. So these two are the pre-states, and these two are the post-states. Right? Pre and post-states. But you'll see once we go to the example. Okay, let's now talk about the first WP rule, the first one. Okay, if you go to the slides, so what I just clarified on slide number 12. All right, so this one has been clarified. And that's the first WP rule. We have an algorithm as simple as a variable assignments, just that. Okay. And let's see the rule. Okay, over here. But before I present to you the rule, which is pretty brief and kind of precise, but let's just do through some example here. Okay, let's think about what we're doing here. So let's say we got our algorithm over here, and then we say x is simply assigned to x plus 1. That's what we're doing here, right? So what we're saying is somehow the post-state value is assigned to the pre-state value of x plus 1. That's what we're saying. Okay? So this will be the pre-state value plus 1. And in the actual post condition, when we say x larger than 0, the x over here, are we referring to the post-state or pre-states? Well, post-state, right? Because it's a post condition, right? Any value you're referring to over here must be the post-state value. We don't really have a way, well, unless you create some duplicate variable, but let's not worry about it. So here, any assertion you're trying to do, you're really saying after the algorithm has been executed and terminated, the post-state value for x must satisfy something, okay? So this is important for you to realize. So this one here is really the post-state value. So now we're clear about pre-state and post-states, and what will be the WP, right? the rule tells you you want to somehow figure out the weakest precondition from which if you try to assign x plus 1 into x so that the post-state value of x is larger than 0. It will be as if you're asserting this particular expression here is going to replace the x over here. That one there is going to be larger than 0. What it is saying is the post-state value over here, we know what this value is in terms of the let me write a little bit better, in terms of the pre-state value. I can definitely do that. Thank you. Just for telling me. Over here. Okay. In terms of the pre-state value. Okay, so let me just do that. Okay, like that. So now for the WP, that's what we're going to do. Let me start with x larger than 0 first of all. Right? I'm just copying the post condition. And this post-state value, I know that is going to be replaced by x plus 1. And the x over here, to be more explicit, is really x0. Right? The pre-state value. So I can simply replace the x over here by x0 plus 1. So this is telling me if my intention is to increment x by 1. And after the increments, I want the post-state value to be larger than 0. It will be as if I'm asserting to say this initial value plus 1, which simulates the increments, is going to be larger than 0, which will be the post condition. Right? So this one will take you some time to really think about. This is more like a base case for WP calculation. So the actual rule tells you you're just going to take the post condition here, and then you're going to replace every free occurrence of x by the expression E. And in our example over here, you can think about R is really x larger than 0. And the E is really the x0 plus 1. And this is the weakest precondition. So this one just kind of illustrates the rule, but we're going to do exercise to see more calculation. Okay. When you review this rule over here, the most critical thing for you to see will be when we talk about the post condition, we are really talking about how the post-state value for the variable should be asserted. How do we know what a post-state value should be? You want to look at the algorithm, and the algorithm itself tells you what that post-state value is assigned in terms of the pre-state value. So we simply do some substitution. Okay? And then we'll do that. Okay? All right, any question here? Yeah?
What does free occurrence in this context mean?
Free occurrence? If you actually look at, well, let's say here, right? X larger than 0, usually free occurrence will be if you got any quantification. If you got quantification, you may have some dummy variable. Let's say dummy variable is actually x. You don't really replace the dummy variable. Only the free occurrence, like what you learned in 1090. So you don't really have any issue about free occurrence if you don't have any universal or existential quantification. But if you only got standalone expression like this, it's automatically free. Okay? Of course, free in the sense what you learned in 1090. Okay? All right. Let's now do some exercise quickly. Okay, the first one, just do one. And another one, you got the answer on the slides. You can also do exercise. Okay, this one here. Okay, what is the weakest precondition for this program to establish this postcondition? Right? So we're going to calculate the WP. Okay, let's now do it right away. So we got our WP over here, and then we say x plus 1. So this is the implementation part. And then the post condition is right here. X larger than x0. Let's get the syntax right first, WP. And in this case, we're reaching the base case for WP. So just apply the rule. So what we do is, so if you like, you can also think about this x over here is really x0. All right? So we're going to say by the WP rule of variable assignment. Okay? So we're going to copy down the post condition, which is x larger than x0, first of all. And then by the rule, we're going to replace every free occurrence of x just by this one here. So think about this is like the E that you will see in the definition. Okay? x0 plus 1. All right? And that one there, what should that be? Right? So what's the free occurrence of x over here? Just the left-hand side. The right-hand side there is actually x0, the initial value. So that's not a x. So what we do is we're going to replace this one here to be x0 plus 1, larger than x0. All right? And then you can easily cancel out both sides. 1 larger than 0. That would be just true. So that means for this particular setup, the weakest precondition is simply true. That means any input value is going to be fine. Okay? If you give any input value incremented, of course it will be larger than the original one. Okay? That's the insight to it. All right, so that's the first one here. And then for the second one, you guys can do some practice over here, right? I'm going to leave that to you. You can find the answer on the slides. Exercise. Okay. All right, question. All right. And then let's now move on to, let me see the next one. Okay, let me also cover another definition here. And on Wednesday, we're going to solve more exercises. Okay, but at least we can go over the definition today. Okay. So the second case for WP calculation is we get the first argument here to be a little bit more complicated, right? Rather than just variable assignments, it's already the recursive case for WP calculation. Okay. So we got if then else. So we got some Boolean condition. And we either go to branch number 1 or branch number 2. So S1, S2. So these are separate programming programming statements, which can be arbitrarily complicated. It's a little bit like a phi that we had earlier, which can be arbitrarily complicated. Okay? And the definition goes like this. To calculate this, we got two cases. Either you can go to S1, in which case you know that B is actually true. Or you might go to S2, in which case you know that B is not true. Right? And we want to say that it doesn't really matter which branch you go to. Either you go to branch number 1, and then you execute S1, or you go to branch number 2, you execute S2. Ultimately, you should really satisfy the post condition no matter what. Okay? That's kind of insight. So this will be the final definition here. Either we go for B or go for not B. Either way. Okay? If you go for branch condition 1, in that way, we want to make sure that particular branch is actually going to satisfy the weakest precondition of WP of S1 to establish R. So this one tells you that going for branch 1 guarantees that R is satisfied. Right? WP calculation. And then if we go for branch number 2, also WP, we got S2 over here, R. You can see the same post condition is being mentioned over here, right? Either you go for branch number 1, you go for branch number 2, doesn't matter. The post condition must be satisfied. The difference is one is talking about S1, the other one is talking about S2. Doesn't matter. Both branches should really be leading to post condition satisfaction. So this one tells you that going for branch number 2 guarantees that R is satisfied. And we require that both branches must be satisfying. It's not optional, right? So this one must be the case, and this one must be the case. So that's why you will see that there's a conjunction. Both branches must establish the post condition R. Okay. Let's do one more thing, and then we'll do more exercises on Wednesday. Okay. But there'll be enough material for you guys to kind of review before Wednesday, so you can also follow up the more. Okay, let's just do one exercise quickly. Okay, this one here. That'll be it for today. Okay. Let's say we're given this particular program here. Let's do some visual annotation here. We got precondition here, and we got postcondition over here. And the middle part here is the implementation. Right? Very clear separation, right? And the question is this program correct? In order to prove or disapprove the program is being correct, we want to prove that whether the corresponding Hall triple is a theorem. Right? That's what we're going to do. So step number 1. And this will be always the step number 1. Doesn't matter how complicated the program is. So step number 1, you want to formulate the Hall triple. Formulate the Hall triple. In this case, the precondition is x larger than 0 and y larger than 0. Right here. And the the implementation, let me write a little bit more briefly for now. Okay. So that one there is going to be if the branching condition, I'll call it B. And this part over here, let me call that S1. And this part here, let me call that S2. And this will involve sequential composition, which I'll speak about in the beginning of Wednesday. Okay. So I'm going to say something like if B, then S1, otherwise S2, N. Right? So this part here just corresponds to this one here. I'm just writing a little bit more briefly. Okay? And then we got the post condition here. We got bigger, larger than or equal to smaller. Okay, let me just leave a little more space for myself. That's the first step. Okay. Now the second step is this. We want to calculate the WP. Calculate the WP for this part over here. Let me call the whole thing over here S. For S, to establish the postcondition right here. Bigger, larger than or equal to, smaller. All right. I'll say a little bit more about step number 2 in a moment. What about after step number 2? We want to make sure the weakest precondition somehow is related to the actual precondition in the right way. Okay, step number 3. Prove or disprove. The actual precondition, which is over here, x larger than 0 and also y larger than 0 is no weaker than the WP. Right? If you look back to the definition for Hoare triple, you will see that. No weaker than the WP. For S to establish bigger, larger than or equal to, smaller. All right, guys, I know I'm running out of time. Give me, how about 2 more minutes, if you don't mind. Okay, I'll do that very quickly. So this is what you're gonna show ultimately. I want to say just a little bit more about the WP here, just by applying the definition quickly. This part over here, okay, that one there, let's now just say S1, S2. Okay, I'm going to talk about how you can handle sequential composition on Wednesday. What can we do a little bit further for the WP here? Okay, here we can say that it's going to be either branch number 1 or branch number 2. X larger than y or x larger than y, not the case. Right, so these are the 2 branches. If the branch number 1 is actually the case, then we got to make sure it implies the WP for S1 to establish the R. Okay, so let me call this one here the R. And also this one implies, okay, sorry about that, but you will see the notes for sure once I publicize that. S2, and then it will be R. And of course, it should be a conjunction between them. Okay, conjunction. Okay, so this will be something you will see ultimately. Either we go for branch number 1 or we go to branch number 2. And when you go for branch number 1, you will see S1. When you go to branch number 2, you will see S2. Both of them should really establish the R. But now for S1 and S2 itself, it contains sequential composition, which we'll learn how to handle on Wednesday. Quite a bit of stuff today, I know, but before Wednesday, try to review the idea about weakest precondition and also Hoare triple. And as we do more exercises on Wednesday, you will also be preparing for your exam. All right, thank you. I'll see you on Wednesday.